Okay, so we're going to get into derivatives a little bit more today, and this stuff really wasn't that bad when we first did it. It's just been a while, and we've been doing integrals a lot, so I just want to go back over this, and this will make doing some test corrections on your take-home test that you did over spring break a lot easier, and the next test will hopefully it'll become a lot easier to do this, but it's just remembering all this stuff. So remember tangent lines. The definition of a derivative is the slope of a tangent line, so there's lots of times that they want you to find the equation of a tangent line. Remember that you need to find the derivative of that function at the point that they give you. You need a point, so you need the y value to go with the x value, and then you just write the equation and you can use slope-intercept form or point-slope form. So I just have an example here. Find the equation of the line tangent to the function g of x equals 3x cubed minus x squared plus 4x minus 2 when x equals negative 1. When you do these, sometimes there's a free response question, and it really isn't, like, this is all it's asking you to do. So tangent line, you need two things. You need a point, so they tell you that x is negative 1, so you need to know what is the y value that goes with that. So what would that be? 3 times negative 1 minus 1 minus 4 minus 2, or negative 10. So here's my point. G of negative 1 equals negative 10. And what else do I need to write a tangent line? I need a slope, and that's my derivative. So I also need the derivative, which would be 9x squared minus 2x plus 4. And I'm trying to find the derivative when x equals negative 1. So I'm going to plug in negative 1 into my derivative, and I would get 9 plus 2 plus 4, or I think that's 15. So now I have my point, and I have my slope, so I'm just going to write my equation. If it's a free response question, don't oversimplify it. Leave it in point-slope form. Y minus y, which is negative 10, equals my slope times x minus my x value, which is negative 1. And there's no need to simplify that. If it's a multiple choice question and it's in slope-intercept form, then obviously you'd want to work it out. But writing tangent lines is definitely something I could expect. I could almost promise you is going to be on the AP test. We also talked about normal lines. Not that big of a deal. I don't think it's going to be on the AP test, but it could. Remember that a normal line is a line that's perpendicular to a function's tangent line at that point of tangency. So we could find that normal line really easily if we already did the derivative of the function. Let me go back for a second. So I still have the same point. It's still g of negative 1 equals negative 10. But it's perpendicular. So what do we know about lines that are perpendicular? About their slopes. Their slopes are negative reciprocals, right? So if we know the slope at negative 1 was 15, then the slope that we're going to use is going to be negative 1/15. And then we're just going to write that equation. So that's going to be y plus 10 equals negative 1/15 times x plus 1. So just remember that normal lines mean perpendicular. All right. What else do we do with derivatives? We also did implicit differentiation, and again, it's something that I could probably guarantee is going to show up on the AP test. Remember that lets you take the derivative when you can't solve for y very easily, and just remember that whenever you take the derivative of y, you have to put dy dx in there, and then you solve for dy dx. And so I think the best way to do this is just to do an example to remind you. So find the derivative of this. Well, the derivative of 4x is just 4. The derivative of x times y, I have to do the product rule. So the derivative of x is just 1 times y, plus, leave the first one alone, the derivative of y is just 1, but we're doing it with respect to x, so we have to put dy dx there. The derivative of negative 3y squared is negative 6y. But again, I took the derivative of y, so I have to put dy dx equals the derivative of 6 is just 0. And remember, we're trying to find the derivative, so we want to know what does dy over dx equal. So I want to get this to the other side, so I'm going to subtract it over, and I'm going to factor out the dy dx on this one at the same time. So if I pull out the dy dx, I would be left with x minus 6y. That would be right there. And I'm going to move the other stuff over, so that's going to become negative 4 minus 1y, or negative 4 minus y. And then the last step is divide that x minus 6y over, so you can get what your derivative equals. And you get negative 4 minus y over x minus 6y. And that is the derivative. What if they ask you to find a derivative at a specific point, like for this one? If it said find the derivative at the point 1, 2, it's just like finding the derivative at a point when it's just x, except for you have to plug in 1 for x and 2 for y and simplify that. So if I was going to do that on this one, I would get negative 4 minus y, which happens to be 2, over 1 minus 6 times 2, which is 12. And I'd get negative 6 over negative 11, or that would be a slope or a derivative of 6/11. So implicit, hopefully, kind of maybe remember that. Inverse functions and derivatives. This is definitely a topic that shows up. Is it going to be on a huge part of the AP test? No. But it could be a question or two on the multiple choice, and they're pretty easy to do if you just know the rule. If a function has an inverse, then the derivative will always be the reciprocal at whatever the point is that's the inverse point on the function. There's a couple ways we can handle these problems. One is if they give you a function that you can actually just write the inverse of, you can just switch x and y, write your inverse function, and take the derivative. But more often, what I've seen on the AP test are questions like what I have down here. And so again, I want to show you this question because I feel like it helps make this rule make sense. They don't give you a function here. It just says f of x contains the point 2, 1, and f prime of 2 equals 3. Find the inverse derivative at 1. So, first of all, remember that the definition of an inverse is if f of x contains the point 2, 1, then we know that the inverse has to contain the point 1, 2. Right? The domain and the range switch. So when they ask us to find the derivative of the inverse at 1, it's going to correspond back to the derivative of the original function at 2. So you got to remember that you have to switch the x and the y. And the derivative will always equal the reciprocal. So 1 over whatever the derivative was at 2 itself, because that was the point where it switched places. So that's all you have to know to do this problem. Since the derivative at 2 was 3, the reciprocal of that would be 1/3. So it's just one of those really little rules that if you remember it, it's going to help you when you're doing that. All right, so those are kind of my derivative rules. The other thing I want to get through today, which hopefully you have some vague memories of, are the critical points, the first derivative test, the second derivative test. And I have a lot of information here. I'm not going to spend a lot of time on it, but this is something I want you looking at when you're going back and doing your corrections, and also when you are taking another take-home test that you can use this to help you. Remember that critical points are where your derivative is equal to 0 or where it's undefined. It's where your relative extrema could occur. Remember, not every critical point is necessarily a max or a min. You have to check it. You have to prove it. On free response, justify your answer means they want to see and they want you to write out the explanation there. So we have a few ways to do this. One way is the first derivative test. That helps you see where the function is increasing and decreasing. Remember, when your derivative is bigger than 0, that means it's increasing. So if your derivative is positive, then that means your graph is increasing. If your derivative is less than 0 or your derivative is negative, that means it's decreasing. And if your derivative is equal to 0, then that means that it's constant. When we do the first derivative test, we usually make those little sign charts, right? Like whatever my critical points happen to be, like A to B. I plug something in and I say, well, I plugged it into my derivative and I got a positive and then a negative and then a positive. That means at A, it changed from increasing to decreasing. And at B, it changed from decreasing to increasing. So I could say that at A, there's a relative max. And at B, there's a relative min. That's the sign chart. That's our intervals where we test it. But when you have to explain your answer or justify your answer, you cannot just use that as your work, right? We've talked about this before. You have to say that the graph of the derivative changed from positive to negative, or the function itself changed from increasing to decreasing at that specific value, or you're not going to get your point on that. And again, reminder, if you go to the next slide here, I just ran out of room. When you test that, if it changes from negative to positive, that means it's changing from decreasing to increasing. That's a relative minimum. And when you test your critical numbers and it changes from positive to negative, that means it's changing from increasing to decreasing. That means it's a relative maximum. I took this, I know this is kind of some small writing, but I copy and pasted this from my little AP Calculus discussion group that I'm on. I thought this was really important. Make sure you answer the question that they ask. It says you need to make sure your students are aware that they need to answer each question with awareness of what is being asked for. A question such as this could ask the students any of the following. Give me the x value where the extrema occurs. That's what we're checking when we do the first derivative test. We're checking the x values. So you would say the relative max occurs at x equals 3. If they actually want the max or the min value, if they ask you for the relative max or the relative min or the extreme values, you're giving the y value that you get when you plug back in. Like, my graph has a maximum of 17 when x equals 3. If they ask you for the point, then you give both the x and the y. It points out here that when they ask you for the extreme values, they really only want the y value. They don't want the ordered pair. If you said the relative max is 7 when x equals 2, I think they'd give you the point for that. But if they ask you for the maximum and you give an ordered pair, I don't know that they'll give you the point for that. So it's really important that you read the directions. And again, notice that the absolute extrema can occur when the derivative is 0 or undefined, as long as you can show that there was a change in sign of our derivative. And we talked about yesterday with the extreme value theorem. Remember that this also could occur at the endpoints of a closed interval. That's the extreme value theorem. All right, so lots of things to kind of keep in mind as you're doing these problems. What else can we throw in here? Second derivative test. Well, remember that the second derivative tells us concavity. So first of all, if your second derivative is positive, then your graph is going to be concave up. If your second derivative is negative, then your graph is going to be concave down. Hand in hand with that are inflection points. Inflection points are kind of like your critical points of your second derivative. It's where the second derivative is equal to 0 or undefined. And if you can show that your second derivative changes sign at your inflection points, then that means that it is an inflection point. Second derivative test, I'm going to kind of draw a line here because these are are two separate things. The second derivative test is never going to be part of the AP test that you have to use, but it's another way to check for relative maximums and relative minimums, and sometimes it's a shorter way. There's one on the homework I'm going to give you today that says use the second derivative test, because I want you to see that it's kind of easier than doing the first derivative test. But remember, if you know what your critical point is, so let's say maybe we should change this to, let's change these to C's, and let's say C equals a critical point. To find your second derivative, or to use your second derivative test, you find your critical points the same way you always have, but instead of making a sign chart and plugging it all back in, especially on a no calculator part, if the second derivative is really easy to find, all you have to do is look at the second derivative, and when you plug your critical point in, look to see whether it's positive, negative, or 0. So if you plug your critical point in and it's greater than 0, well, that means it's concave up, and because it's a critical point, that means it has to be a relative minimum. If your second derivative, when you plug in your critical point, is negative, that means it's concave down, so that means it's a relative maximum. But most people aren't a big fan of the second derivative test because sometimes you get 0, which means it fails, and you have to go back to the first derivative test anyway. Like I said, there's one on the homework today that I want you to do the second derivative test just to remind you of. But if you feel like you're just going to get that confused with the first derivative test on the AP test, you don't have to use it. The first derivative test really does work all the time. Okay? And then the last thing I want to talk about derivatives is something that we're going to talk about over and over again. But remember that position, velocity, acceleration. I can promise you that you're going to see multiple questions on both the free response and the multiple choice over position, velocity, acceleration, and a whole bunch of different stuff. This is not the only time we're going to talk about this, but just a little reminder that if I use s of t for my position function, that when I take the derivative of that, I get the velocity. Remember that we can tell where the velocity is moving left, right, and stop by using the critical points. Like where my velocity is greater than 0, the particle is moving to the right. Where my velocity is less than 0 is moving left. And your critical point, where your velocity equals 0, is where that particle is stopped. Also remember that especially using integrals, we can find like how far it's traveled. If you take the integral from like a to b of your velocity function, you can find that ending position, but don't forget that you have to take into consideration the initial position. And another one that shows up a lot is total distance. Remember that total distance traveled, we kind of forget about the whole positive and negative, so we take the absolute value of the velocity function, and we'll go over that again as we go into this further. You can also find the maximum height, especially if we talk about the velocity of some object or a rocket or something, because the maximum height is going to occur where the maximum occurs of the function itself. So you can find the critical points and you can figure out which one is a maximum, and then plug that back in to find the y value that goes with it. And then acceleration, remember, is the derivative of the velocity function, or the second derivative of the function itself. And there's lots of problems with that, and we'll go through some of those. What I have for you today is a little worksheet. It's from a little book that I have that's just reviewing topics, so it's kind of just a couple questions of each one of these. Some derivatives. I have some chain rule on there, some product rule, some quotient rule, but also some implicit and some stuff about max and mins, just to kind of refresh your memory. So that's your homework for today, and that'll be due tomorrow.